We will now continue our study of capacitance by looking at the role played by the dielectric in determining the capacitance of the capacitor, and then we will look at how we can produce different values of capacitances by suitably combining capacitors either in series or in parallel. Let's start by looking at the role played by the dielectric in determining the capacitance of a capacitor. Well, consider a capacitor that is charged with one plate positive and the other negative, separated by air between them. This is a capacitor where one plate is charged positively and the other plate charged negatively. Obviously, there is an electric field in between the two plates. Alright, tell me, what is that electric field equal to? What is the equation for the electric field in between two parallel plates, one charged positive and the other charged negative? It is sigma over epsilon naught, where sigma is the charge density on the plates. Alright, the electric field between the two plates, we are now going to represent it by E0. Now that means this is the initial electric field before we place a dielectric. At the moment you have air between the capacitor plates. Now, what happens when a dielectric medium is introduced between the plates? Let's introduce a dielectric and see what happens. Well, I have now placed a dielectric in between the two plates, and see what happens. Although there are no free charges in the dielectric, displacement of positive and negative molecular charges occur in the dielectric near the capacitance. You see, there are no free charges, so that charges can move, so that polarization can happen. But in the dielectric, with atoms and molecules near the positive charge, will orient in such a way that the negative charges will be facing the positive plate and the other end will be facing the other way. Similarly, the end of the dielectric facing the negative, there will be positive charges aligning at this end and negative on the other end. So these are called bound charges. The charges that appear on the dielectric, they are not free to move. Therefore, we call them bound charges. They cannot move about. So, here you have the negative charges appearing on the side of the dielectric that is close to the positive plate, and positive charges appearing on the side of the dielectric that is close to the negative charges. What do you call these charges? The bound charges. Well, these bound charges are now going to produce an electric field directed in the opposite direction as that of E0. Remember, before the dielectric is placed there, the electric field was from the positive plate to the negative plate. When the dielectric is introduced, these bound charges are going to produce an electric field in the opposite direction. These bound charges produce an electric field E prime that opposes E0. Now, here I have represented that E prime by these yellow lines. This is the E prime, that means the electric field produced by the bound charges. Now, therefore, what is now the net field in between the capacitor plates? There is an original field E0 caused by the charges on the capacitor plates. Now, after the dielectric is introduced, the bound charges on the dielectric produces an electric field E prime that opposes the original field E0. That is our E0. The net field E between the capacitor plates now will be, what will that be? Will be E0 minus E prime. That will be the net field now between the capacitor plates. The net field E is related to kappa. Now, how is the net field related to kappa? E equal to E0 divided by kappa. That means if kappa is very large, this resultant field will be small. And that is how it influences the capacitance of the capacitor. Now, if kappa is 1, then the net field and the original field will be the same. In other words, there will be no E prime. But if kappa is 2, then the net field E will be half of the original field. And if kappa is 3, then the net field will be 1/3 of the original field. Suppose sigma B represent the bound charge. You see, bound charges are the charges on the dielectric. If sigma B represent the bound charge density and sigma F represent the free charge density, well, the free charges are on the capacitor plates. So sigma F is the surface charge density on the capacitor plates. Sigma B is the charge density on the dielectric, the bound charge density. Then we can say E0. That means the electric field between the capacitor plates before the dielectric is introduced is sigma F divided by epsilon naught. I hope you remember that equation. The electric field between two parallel plates is sigma over epsilon naught. So E0 is caused by the free charges. Therefore, that will be sigma F divided by epsilon naught. And E prime, the electric field caused by the bound charges, will be sigma B divided by epsilon naught. Now, let's do a problem. Two parallel plates have charges Q and negative Q. When the space between the plates is devoid of matter, well, that is free space, the electric field is 2.5 times 10 to the 5 volt per meter. When the space is filled with a certain dielectric, the field is reduced to 1.2 times 10 to the 5 volt. Now, you can see this is E0. Is that right? The original field. Now, what is this? Is it E prime or E? Well, when the dielectric is introduced, the field is reduced to, that is the net field, which is E0 minus E prime. It is reduced to 1.2 times 10 to the 5 volt per meter. What is the dielectric constant of the dielectric? If Q equal to 10 nanocoulomb, what is the area of the plates? What is the total induced charge on either side of the dielectric? In other words, what is the total bound charges? Okay, let's see what is given. You are given E0. E0 is 2.5 times 10 to the 5 volt per meter. You are given E. E equal to 1.2 times 10 to the 5. What does E represent? The net field E0 minus E prime. QF, the free charges on the capacitor plates, is 10 nanocoulomb. And E equal to E0 minus E prime. You know E, we know E0, therefore we can find E prime. Therefore E prime, what does E prime represent? E prime is the electric field within the dielectric, the field produced by the bound charges. So E prime is E0 minus E. That will be 2.5 times 10 to the 5 minus 1.2 times 10 to the 5. And that is 1.3 times 10 to the 5 volt per meter is the electric field due to the bound charges. Now we need to find the dielectric constant of the dielectric. Now, can you recall an equation for that? Well, E, the net field, equal to E0 divided by K. Now, we know the net field, we know the original field, and therefore kappa equal to E0 divided by E, and that will be 2.5 times 10 to the 5 divided by 1.2 multiplied by 10 to the 5, and that will be 2.08 is the value of the dielectric constant. Okay, what's the next question we need to answer? If Q equal to 10 nanocoulomb, we have that is the free charges. What is the area of the plates? Well, we have E0 equal to sigma F over epsilon naught. That will be sigma F is the charge density of the free charges on the capacitor plates, and that will be the total charge on the capacitor plates divided by the area of the capacitor plates. So I replace sigma F by QF divided by A, and so E0 equal to QF divided by A divided by epsilon naught, and this A will come to the denominator. That will be QF divided by A epsilon naught. Now we have E0, we have QF, we have epsilon naught. Therefore, we can find the area of the capacitor plates. Well, area equal to QF divided by E0 epsilon naught. Q0 is 10 to the negative 8 coulomb, 10 nanocoulomb, and E0 is 2.5 times 10 to the 5 volt per meter, and of course epsilon naught. And that gives me the area of the capacitor plates is 0.0045 meter square. Well, we need to find we found the area of the plates. What else do we need to find? What is the total induced charge on either side of the dielectric? Well, we know that E prime equal to sigma B divided by epsilon naught. E prime is the electric field inside the dielectric caused by the bound charges. So E prime equal to the bound charge density divided by epsilon naught, and the bound charge density is the amount of charge, the amount of bound charge, that means the amount of induced charge in the dielectric, QB divided by A over epsilon naught, and that A will come down. And do we know A? Yes, we know A. We calculated that in the previous slide. Now, therefore, QB equal to E prime A epsilon naught. We calculated A. A is 0.0045 meter square. So E prime is given to be 1.3 times 10 to the 5. And this is our area. And this is epsilon naught. And therefore QB, the bound charges on the dielectric is 5.75 times 10 to the negative 9, and that is the total induced charge on either side of the dielectric, and that will be 5.75 nanocoulomb. Okay, we will now talk about capacitors connected in series. Now, what is the meaning of connecting capacitors in series. Well, here I have connected 3 capacitors in series. I want you to learn how capacitors are connected in series. Now, this capacitor has a capacitance C1, this has a capacitance C2, and this has a capacitance C3. Now, I have placed them in such a way that the positive of the first capacitor, negative of the first capacitor. The negative of the first capacitor is connected to where? The positive of the second capacitor. The negative of the second capacitor is connected to the positive of the third capacitor. And the negative of the third capacitor is connected to the negative end of a battery. The positive end of the capacitor, the first capacitor, is connected to the positive end of the battery. Now you can see there is a closed electric circuit here that contains 3 capacitors connected. Now watch or listen to the terminology I use. 3 capacitors are connected in series, and that series combination is connected across a battery. Now, what is the function of a battery? What does the battery do? We will talk more about it in the next lesson, but the function of a battery in an electric circuit is to provide the necessary potential difference. You see, electric charges can move only if there is a potential difference. And the potential difference necessary for moving the electric charges are provided by this battery. Now, in this case, when the positive of the battery is connected to the positive of the first capacitor, electric charges move from the battery so that this plate of the capacitor, this plate of the capacitor receives a positive charge. Now I'm going to disconnect it because the charges are, and now if this receives a positive charge, then this will be receiving a negative charge. Now if this receives negative charge, the one that is connected to the because this is connected to the next capacitor, these negative charges are drawn from this plate, leaving this plate positive. You see that? So this becomes positive, means this will become now negative. Now this is connected to the terminal of this capacitor, so what will be the polarity of this? That will be positive. That means each of this capacitor will have a positive plate and a negative plate. So this is the positive plate, this is the negative plate, this is the positive, this is the negative of the second capacitor, this is the positive and this is the negative of the third capacitor. So how are they connected in series? The negative of the first capacitor is connected to the positive of the second. The negative of the second capacitor is connected to the positive of the third. And the negative of the last and the positive of the first comes back to the battery. Now what does the battery do? The battery provides a certain amount of charge Q to the first capacitor plate. Now that means if this has a charge Q, then this will have a charge negative Q. If this has to have a charge negative Q, that means the plate that is connected to that of the second capacitor will then obtain a positive Q. If this has a positive Q, the other plate for the same capacitor will have negative Q. Now if this has negative Q, the plate that is connected to that of the third capacitor will have positive Q. You see that? So the amount of charge on the first capacitor plate is positive Q, other plate negative Q. This is positive Q, negative Q, positive Q, negative Q. And now This is a bike battery, and most of you know it is 6 volt. So I have applied a potential difference of 6 volt. What does that mean? Volt means joules per coulomb. In other words, when this battery is connected, the amount of work done to move 1 coulomb of charge from one end of the circuit to the other will be 6 joules. 6 joules per coulomb. So, if I want to move 1 coulomb of charge now through this system, the amount of work done for 1 joule will be 6. The amount of work done for 1 coulomb will be 6 joules. That's the meaning that the potential is V. Now, that means the amount of work done, you remember the charge has to go through capacitor 1, then capacitor 2, then capacitor 3. So this total work done is actually divided into 3 parts. 1/3 of the work is done in order to transport that charge across the first capacitor. Then a certain amount of work is done to transport the charge across the second capacitor. Then you need to do work to transport the same charge across the third capacitor. So the total amount of work done is a measure of the work done to move the capacitor. The total amount of work done is a measure of the work done to move the charge across the first capacitor plus the work done to move it across the second capacitor plus to move it across the third capacitor. That means the potential difference now across each of these capacitors, if you add the potential difference across this, add it to the potential difference across the second capacitor, add it to the potential difference across the third capacitor, it must be equal to the total potential difference. Now that means when capacitors are connected in series, they divide the total potential. If the total potential is 6 volt, if each of these capacitors is the same, then each will have 2 volt across each of them. The potential difference across the first one will be 2 volt. The potential difference across the second one will be 2 volt. The potential difference across the third one will also be 2 volts. So that the total potential will be V1 plus V2 plus V3. So let me repeat that again. If a parallel network of capacitors are connected across a battery that provides a potential V, I'm not going to give you a number now. If the total potential is V, then that total potential will be divided among the 3 capacitors. So that if the potential difference across the first capacitor is V1, the potential difference across the second capacitor is V2, and the potential difference across the third capacitor is V3, then V1 plus V2 plus V3 will be equal to the total potential provided by the battery. Okay, now let's write those things down and obtain an equation for the total capacitance. If 3 capacitances are connected in series, what is the total capacitance in the circuit? Alright, let's look at that and we will now write that down. As I showed you, we have 3 capacitances of capacitance C1, C2, C3 are connected in series and the combination is connected to a battery. You see, a battery has a positive end and a negative end. The battery provides a total potential V, and I told you that this total potential will be now divided among the 3 capacitors as V1, V2, V3, so that V1 plus V2 plus V3 will be equal to V. Alright? And so the total potential will be divided so that the potential difference across C1 will be V1, across C2 will be V2, and across C3 will be V3 in such a way that V equal to V1 plus V2 plus V3. But as I explained to you, if a total charge Q is taken from the cell, that charge Q is on the first capacitor plate. If this gets a positive Q, then its other plate will have a negative Q. The second capacitor similarly will have a Q, a negative Q, Q, a negative Q. What that means is each capacitor has the same amount of charge, and that is equal to the amount of charge removed from the battery. You see that? Each capacitor will have the same amount of charge Q, and that is the total charge that is removed from the battery. So the total potential gets divided, but the total charge remains the same throughout that circuit. This is an important characteristic of series connection. When capacitors are connected in series, the total potential divides among the capacitors, but the total charge will remain the same throughout the circuit. Therefore, you can see if Q is the amount of charge, amount of positive charge on capacitor 1, then it will have a negative Q on the negative plate and a positive Q on the second capacitor and negative Q. Similarly, positive Q will be on the positive plate of the third capacitor and negative Q on its negative plate. When capacitors are in series, all of them will have the same charge. The same charge Q, which is the total amount of charge that is removed from the battery. So, this is the potential equation. V equal to V1 plus V2 plus V3. Now, let's divide this equation by the quantity Q, because Q is the same for all. Let's divide this equation by Q. Dividing means divide each term. So that will be V divided by Q equal to V1 divided by Q plus V2 divided by Q plus V3 divided by Q. Well, I hope you remember the fundamental equation of the capacitance, which is C equal to Q over V. Is that right? That is the fundamental equation for capacitance. Capacitance is Q over V, where Q is the total charge and V is the total potential. Therefore, can you tell me what is this V over Q equal to? If Q over V equal to C, what is V over Q equal to? V is the total potential and Q is the total charge. Therefore, V over Q must be 1 over C. Is that right? Yes. So because Q over V equal to C, then V over Q must be equal to 1 over C. And what will then be V1 over Q? V1 is the potential difference across the first capacitor and Q is the charge in it. Therefore, V1 over Q will be 1 over C1. There you are. Similarly, V2 over Q will be 1 over C2. And V3 over Q will be 1 over C3. So what does this equation now become? It will become 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. And this is the expression for the total capacitance. Look at this. This C represents the total capacitance. When three capacitors of capacitances C1, C2 and C3 are connected in series, the total capacitance C will be such that 1 over C equal to 1 over C1 plus 1 over C2 plus 1 over C3. Alright, let's see what happens if two capacitors, instead of connecting three, suppose if two capacitors are connected in series, what will be the total capacitance of that combination? Well, 1 over C will be equal to 1 over C1 plus 1 over C2. Can you simplify and solve for C from here? What will be C equal to? If you simplify this, C1, C2 is the common denominator, and the numerator will be C2 plus C1. So simplifying this gives you C1 plus C2 on the numerator divided by C1 times C2. If 1 over C equal to C1 plus C2 over C1 C2, what is C equal to? C will be the reciprocal. C therefore equal to C1 C2 divided by C1 plus C2. When two capacitors of capacitances C1 and C2 are connected in series, the total capacitance of the combination C equal to C1 C2 divided by C1 plus C2. A very important relation. Now tell me if you know what that relation is. When capacitors are connected in series, will the total capacitance be greater or smaller than any of the capacitors we used here? What do you think? Well, take an example. Suppose I use C1 equal to 5 and C2 equal to 10. Alright? If C1 equal to 5 and C2 equal to 10, what will then C equal to? Let us say C1 equal to 5 microfarad. C1 is 5 microfarad and C2 is 10 microfarad. Then C will be equal to C1 times C2 will be 5 times 10, 50 divided by C1 plus C2 will be 15, and that will be approximately 3.33 microfarad. So when a 5 microfarad capacitor and a 10 microfarad capacitor are connected in series, the total capacitance of the system is C1 C2 divided by C1 plus C2, 50 divided by 15, that is 3.33 microfarad. The total capacitance is smaller than the smallest of the capacitors used. So tell me, what is the use in connecting capacitors in series? Why do you want to do that? Well, sometimes you may need a value of a capacitor that is not in your stock. You want a very small value of the capacitor that is not in your stock. You can obtain the desired value by connecting 2 or 3 or 4 high value capacitors in series to give you your desired value of the capacitance. So that is the idea of connecting capacitors in series. When capacitors are connected in series, the total value of the capacitance will be less than the smallest of the capacitors used in the circuit. Capacitors are connected in series when you need a smaller capacitor than the ones you already have. Let's do a problem. A 10 microfarad capacitor is connected in series with a 20 microfarad capacitor, and the system is connected across a 6-volt battery. Find the equivalent capacitance of the combination. B. What is the charge on each capacitor? And C. Find the potential difference across each capacitor. Well, that's not difficult. This is the situation. You have two capacitors, 10 microfarad and the other 20 microfarad in series, and the combination is connected to a 6-volt battery. Find the equivalent capacitance of the combination. Well, if C1 equal to 10 microfarad and C2 equal to 20 microfarad, what is the equivalent capacitance? The equivalent capacitance C will be C1 C2 divided by C1 plus C2. Now let me caution you, this equation can be used only if you have two capacitors. If you have three, you cannot extend this equation for that. This is useful only for two capacitors. So when you have two capacitors in series, the total capacitance is C1 C2 divided by C1 plus C2, and that will be C1 is 10 microfarad, C2 is 20 microfarad divided by 10 plus 20. What is that equal to? That will be 200 divided by 30. That will be 6.67 microfarad. You see, when capacitors are connected in series, the total capacitance will be smaller than the smallest of the two. The smallest of the two is 10. The total capacitance is less than that. So your total capacitance is 6.67 microfarad. What is the next thing we need to find? What is the charge on each capacitor? Well, in order to find the charge, you need to know the potential difference. Is that right? Well, the charge on C1 equal to the charge on C2 equal to the total charge. You see, when capacitors are connected in series, the total charge in the circuit and the charge on each capacitor will be the same, because it's the same charge that flows from one capacitor to the other. So the total charge will be the same as the charge on C1, will be the same as the charge on C2. Is there any way to find the total charge? Well, yes, there is a way. What is it? We know the total capacitance. We know the total voltage. Well, if you know the total capacitance and if you know the total voltage, can you find the total charge? Yes, Q equal to CV. Is that right? If Q is the total charge, then Q equal to CV, where C is the total capacitance and V is the total potential. The total potential is 6 volt and the total capacitance is 6.67 microfarad. Therefore, the total charge Q equal to 6.67 times 6 volt, that will be 40 microcoulomb. 40 microcoulomb is the total charge in the circuit, and each of the capacitors has the same amount of charge. So what is the charge on each capacitor? The answer is, the charge on each capacitor is 40 microcoulomb. Find the potential difference across each capacitor. Well, you know the charge on capacitor 1. How much is it? 40 microcoulomb. You know the capacitance of the first capacitor. Well, if you know the capacitance and the charge on the capacitor, can you find the potential difference across the plates of the capacitor? Yes. V equal to Q over C. Is that right? Yes. So V1 equal to Q1 over C1. Q1 is 40 microcoulomb. C1 is 10 microfarad. So that will be 40 divided by 10. That is 4 volt. The potential difference across the first capacitor is 4 volt. If you now understand the mechanism of a series connection, you could tell me the other one right away. What is the potential difference across the second capacitor? Well, the total potential is divided. The potential difference across the first capacitor plus the potential difference across the second capacitor must be equal to the total potential. So the total potential is 6 volt. The potential across the first capacitor is 4 volt. So what must be the potential across the other capacitor? It must be 6 minus 4, that is 2 volts. Well, we can find the same answer by going this way. If V1 equal to Q1 over C1, then V2 must be equal to Q2 divided by C2. There you are. And Q2 is the same as Q1, is the same as the total charge. So Q2 is 40 microcoulomb, C2 is 20 microfarad. That will be 40 divided by 20 is 2 volts. You can see here the total potential across the two capacitors equal to the total potential provided by the battery. Okay, well, I'm going to make this a small lesson, and the next part is capacitors connected in parallel. I'm going to get back to you with that lesson a little later.